So this section is on oscillations and waves, and so we'll start with an oscillation. An oscillation is periodic motion that is otherwise stationary. So, for example, a pendulum. Let me try again on this. A pendulum just rocks back and forth, right? And so it just rocks back and forth. Or you could have a weight hanging from a spring, right? That if you pull it down and release it, like a slinky, you probably can't, I don't think I'll be able to demonstrate that here anyway. But any motion that's repeated, but it's otherwise stationary. In other words, the oscillation is taking place, but it's otherwise staying in the same location, right? The pendulum isn't moving. Here's a slinky, and you probably can't see that, but the slinky just rocks up and down as the spring pulls in the opposite direction. If you remember, the force due to a spring from Hooke's law is minus kx. This was Hooke's law. And so this is the force due to the spring. The force to pull the spring is just kx, but the force due to a spring is this, and you can kind of see it on my slinky here. So if I hold this end fixed, if I stretch the spring out, it pulls against the direction I was stretched, right? Or it's just hanging like this and I push it up, you really can't see that. It pushes down. If I pull down on it, it pulls up. And so the minus sign means the spring opposes its displacement. That's the displacement, right? That's the displacement. And so if I pull it out, it pulls in. If I push it in, it pulls in, pushes out. Same thing with the pendulum. If you swing a pendulum out to the side, it wants to go back the other way. It's always trying to get back to its equilibrium position. And so as a result, when you take objects like this and displace them from the equilibrium position, you get oscillation, right? It keeps swinging back and forth. This just swings up and down, each time going past its equilibrium position until friction brings it to a stop. So that's what an oscillation is. And so we have two of these, and so we'll just talk about these two examples. So for an oscillating spring, you've got a mass on a spring. We'll do it horizontally, just for the sake of this discussion, so it doesn't get too complicated. That way we can ignore what gravity, the effect. If I hold it vertically, if we do it vertically, then gravity is acting too. But here, the spring is pulling this way. The force due to the spring is either this way or this way. If I compress it, the spring pushes out. If I stretch it, the spring pulls back in. And so if this is a mass m and the spring has constant k, then when this oscillates, then the period of the oscillation, that is to say the time for one oscillation, is 2 pi times the square root of m over k, where m is the mass and k is the spring constant. So what's the spring constant if the mass is 0.1 kilograms or 100 grams, and the spring constant is 1,000 newtons per meter, right? That's what the stiffness of the string is, right? And so we can say, well, the period is 2 pi times the square root of 0.1 kilograms over 1,000 kilograms, which is newtons per meter, right? That's the units for K, right? And so that becomes 2 pi times the square root of, so 0.1 over 1,000 is 10 to the minus 4. If you remember, a newton is a kilogram meter per second squared. And so the meters and the meters cancel. That gives me a kilogram per second squared in the denominator. The kilograms cancel. I get a second squared in the numerator. And so this is 2 pi times 10 to the minus 2 seconds, right? And that's about 0.628. Let's see, sorry. The period is 0.0628 seconds. In other words, it's 2 pi, which is 6.28 times 10 to the minus 2 seconds. Right. Okay. Let's pick a period that's a little rounder number. Let's assume that the period is 0.1 seconds, right? What is the frequency? Well, the frequency is the number of oscillations per time. And so if it's 0.1 seconds per oscillation, then that means there are 10 oscillations per second. Do you follow that? If it takes 0.1 seconds for an oscillation, and that means the number of oscillations per unit time, if we pick seconds, is 10, right? The number of oscillations per hour would be like 36,000 or something like that. But if 0.1 seconds for one oscillation, that means 10 oscillations per second. And so the frequency is just 1 over the period. And so if you know the period, you can calculate the frequency. If you know the frequency, you can calculate the period. Right? Also, this is sometimes called 10 hertz. A hertz is a 1 over a second. So whenever you hear, like, the coyote is 95.5 megahertz, that's million oscillations per second. So that's what that means. So there's an example of how to calculate the period and the frequency for a spring, and now let's do it for a pendulum. So we're going to talk about the frequency and period of a pendulum. And so now we've got a pendulum. It's got a mass m. It's going to do that. The string is length L, and we'll call it a simple pendulum. And what that means is that we assume the spring has a string. No, it's not a spring, it's a string. We assume the string has no mass and length L, and the mass is a point mass at the end of mass m. And so it's an idealized, a typical pendulum will have some mass up here too, but we just assume it doesn't. So this is what we call a simple pendulum. So in this case, the period is 2 pi times the square root of L over G. And so So we're going to pick a simple pendulum with a mass of 0.1 kilograms and a length of 1.0 meters. And so the period is equal to 2 pi times the square root of 1 meter over 10 meters per second squared, right? Which is equal to 2 pi times the square root of 10 to the minus 1 second squared, which is approximately 2 seconds. The period is time to go over and back. That's one cycle, and that's what this is. And you can sort of calculate this. This is square root of 10 is about 0.316, and when you multiply that by pi, you get about 1. And so then when you multiply that by 2, you get about 2. And so the period is about 2 seconds. A couple of things to notice here. First of all, the mass didn't matter, right? The period of a pendulum does not depend on the mass. You'll probably do a lab at some point that will test that. But it's true, and it was first noticed by Galileo, who was watching the chandeliers. They had windows in their churches, and they had chandeliers at the top, and sometimes the wind would cause the chandeliers to rock, and he would be sitting in church, maybe as a child, a little bored perhaps, and he would watch the chandeliers and compare their rocking motion to his heart rate. And he noticed on windy days, when they were rocking far, they took just as many swings compared to his heart rate as when they were rocking softly and gently. And that made him think that pendulums would be good, useful tools as clocks, because they seem to not have much variation. They seem to be very consistent in their rocking motion. And so Galileo played a big role in the invention of the pendulum clock. So this is an example. By the way, in the section we did on springs, we didn't talk about it, but the spring doesn't depend on how far back you pull it. And neither does this one, by the way. Notice there's no information in the period on how far back it was swung. Right? The mass doesn't matter, and how far back doesn't matter. All that matters is the length. And so hopefully you'll experience that. So for the spring, the mass does matter, but how far you pull it back doesn't matter. And how long the spring is doesn't matter. Okay. That's the pendulum. Oh, so we can calculate the frequency for the pendulum. Again, once you know the relationship between the frequency and the period, the frequency is just 1 over a period. And so this is 0.5 per second, or 0.5 hertz. If it takes 2 seconds for one oscillation, then you get 0.5 oscillations per second. That's what this is saying. The frequency is just the inverse of the period. This is seconds per oscillation. This is oscillations per second. So they're just 1 over each other.